Welcome to the next lesson in the course Measurements in Engineering. In this short video, we will see how to measure another non-electrical quantity, which is speed. The first task we have here is a measurement of the speed of a DC motor using a Hall sensor. This Hall sensor is located above the DC motor and a small cogwheel. By rotating the cogwheel, the sensor output will produce a square wave. That indicates a time when there is a tooth under the Hall sensor and when there is a gap. The wiring diagram of the test setup is quite simple. To be able to detect sensor pulses, we have connected a pulse counter, the top right box here. We also have a power supply, which is the box at the bottom right. The voltage source is used to supply the DC motor, and the set voltage is directly proportional to the motor speed. Depending on the speed, the given pulse frequency from the Hall sensor is then displayed on the pulse counter. The Hall sensor is intentionally positioned using a threaded rod. When I rotate the threaded rod, I can change the distance between the top of the sensor and the cogwheel. This makes it possible to achieve a larger air gap between the cogwheel and the top of the sensor. In practice, it is important to set this distance between the detected object and the sensor close enough so that the individual teeth are not omitted. If the sensor is too far from the object, it may start to skip some teeth. This leads to the measurement of the wrong pulse frequency and thus the speed of the motor. I will now start the DC motor and keep its speed constant. I can immediately see on the pulse counter that the number of detected pulses is roughly constant as well. Because the cogwheel has 15 teeth on it, one revolution will represent 15 pulses. So, to calculate the DC motor speed per second, I would have to divide the displayed number by 15. In addition to the pulse counter, I could use a so-called stroboscope and get the motor speed with the help of the stroboscopic effect. If I manage to synchronize the frequency of the flashes emitted by the stroboscope with the frequency of the rotation of the motor, the rotating cogwheel will appear to be at a standstill. Now, if we have a constant speed of the motor and I start moving the distance of the Hall sensor from the cogwheel, then you can see that from a certain distance, the detected frequency starts to differ. This means that the Hall sensor is too far from the cogwheel and it is starting to lose some teeth. Instead of a pulse counter, an oscilloscope can be used as a proof that the pulses are really being lost. Here, the output of the Hall sensor is displayed as a function of time. If the distance is correct, there are no missing pulses, no matter what time range I look at. As soon as I start to increase the distance of the sensor from the cogwheel again, some of the pulses start to disappear. If we stop the oscilloscope, we can see that somewhere the sensor evaluates the presence of a tooth, while somewhere the presence of an air gap. If I use the dimensions of the threaded rod, I can calculate what is the maximum working distance of the Hall sensor from the cogwheel, and I should not exceed it in my target application. In practice, these sensors are used for various purposes. One of them is, for example, measuring the speed of a car. In this case, the sensor is located behind the car's wheel. Then, there is a similar mechanism as a cogwheel. The sensor counts the pulses and then evaluates the speed of the car. This information is sent to the car's central unit. Another example of the speed measurement is done by using an incremental speed sensor, so-called IRC. A wiring diagram of the test setup is visible here. Let's look on the real setup. The IRC sensor is connected via a coupling to the DC motor. Two outputs from the IRC are connected to the oscilloscope, and the voltage source can again set the speed of the motor. As soon as we turn on the oscilloscope and the motor, we can see that the output pulses have a certain shape. Another thing you may notice is that the outputs are shifted in time. In other words, that there is a phase shift between these two signals. Each IRC has a defined number of pulses per revolution, and the design can differ. For example, if we have 8-bit IRC, the number of pulses per revolution from one output will be 256. While if we have a more accurate 10-bit IRC, the number of pulses will be 1024. As in the previous case, the number of pulses represent the motor speed. So if we have 8-bit IRC and we will divide the pulse frequency with 256, we will get the motor speed. One of the advantages that the outputs are shifted to each other in time is the fact that if I change the direction of the motor rotation, the phase shift of the displacements changes too. We can easily confirm this by swapping the DC motor power terminals. As soon as I do this, I can see the change of signals detection at the oscilloscope. One more time, I will swap the voltage and I can see the shift change. Here's another detail of the swap, and we can immediately see how the displayed waves shifts. So if your target application requires knowledge of the motor direction of rotation, you can make some kind of an evaluation algorithm that will detect it. I could measure the speed again with the stroboscope and compare it with the detected signal frequency. Instead, I can use another device known as the optical tachometer. In this case, the digital tachometer emits a steady light that does not flicker. If this light is reflected from the measured object back to the photodiode, it is registered. On the contrary, not enough light intensity reflected back, no pulse is recorded. The tachometer then calculates the speed of the measured object from these pulses over time. We can see its application here on the motor's clutch. Because the clutch has a cardboard glued on it, which consists of light and dark parts, the tachometer calculates the motor speed based on the reflected and non-reflected light. So in case of IRC, it is important to remember that in addition to the possibility of calculating the motor speed, the IRC output can also be used to detect the direction of rotation and also the rotor relative position. Now we have the last example ahead of us. The overall wiring diagram is a bit more complicated, so let's describe it in the real picture. Here a DC motor is coupled with a dynamo. You can think of the dynamo as a simple DC generator. If the dynamo is rotated by the motor, then there will be a measurable voltage at the output of the dynamo. This voltage is directly proportional to the speed of the DC motor. What we have here next is a voltmeter, oscilloscope and a resistive load. As in the previous two cases, I could verify the speed of the motor by stroboscope, digital tachometer, or by pulse counter that is connected to the optical sensor located next to the cogwheel. The dynamo has a nameplate on it, and if I wanted to know in advance the dependence between the induced voltage and the speed of the dynamo, I could find out this information right here. I will now run the motor to achieve a constant speed. Immediately I can see that the induced voltage is measured on the voltmeter. This time the cogwheel that is connected to the DC motor has 60 teeth per revolution. Therefore, to get the RPM value, I would have to divide the displayed frequency by 60. Based on the motor speed and the magnitude of the induced voltage, I can draw the so-called steady-state characteristic, which gives me the ratio between the change of speed over the change of induced voltage. When measuring this characteristic, it is important to remember that it corresponds to the actual measurement conditions. If I change the measurement conditions, e.g. by connecting a resistive load to the output of the dynamo, the motor speed decreases, as does the magnitude of the induced voltage. Under these conditions, if I draw a new steady-state characteristic, it would not correspond to the original one. The ratio between the change of speed over the change of induced voltage is now different too. What you should remember from this last example is that if you already have a calibrated output from a sensor, you do not change the measuring conditions. Otherwise, as in this case, the characteristic between the measured voltage and the motor speed could be lost.